Okay, well, this is for the people that aren't here today. We'll record this here. Let's just go through all the different intervals here with this handout. And if you haven't done so already, I would encourage you to write in each interval what is happening. So what is happening from 0 to 5 seconds? Speeding up. Right? Each interval is 5 seconds. Can I write on there? Okay, so from 0 to 5 seconds, it's speeding up. How do we see that it's speeding up on the DT graph? Curved. Speeding up, how do we see that on a VT graph? Straight and increasing away from 0, right? How do we see speeding up on an acceleration time graph? Flat. Right? This indicates that the acceleration is positive. Now, can you tell, if I only showed you, and in the good old days I'd do this with my overhead, but I can't do that. If I only showed you the acceleration time graph, can you tell just from this that the object is speeding up?
Because the velocity could be going in a different direction.
For example, this one here, Joy?
Yes.
Exactly. Well done. Here the acceleration is positive, but the velocity is negative, so the vehicle is slowing down. So you can't just tell from the acceleration time graph whether it's speeding up or slowing down. You need it in conjunction or in addition to the velocity time graph, right? The signs have to be the same. Positive, positive, speeding up. So if you haven't written in between 0 and 5 seconds speeding up, you should do so. What's happening from 5 to 10? Constant velocity. How do we tell that from the DT graph? Straight line. How do we tell it from the VT graph? Constant velocity? Flat line. How do we tell it from the acceleration time graph? Flat line at 0. Can you tell just from the acceleration time graph that it is not going faster or slower? Can you tell from the acceleration time graph that it is not just going faster or slower? Yes, you can, because it's 0. Acceleration 0 means it's not speeding up, not slowing down. Can you tell if it's stopped or not? No. It could be stopped or it could be constant velocity. Well done. What's happening between 10 and 15? Slowing down. How can you tell, Peyton, from the DT graph? The curve is flattening. Okay, you're right. Curve is flattening, so it's slowing down. How can you tell it's slowing down from the velocity time graph? Does it have to be going down to be slowing down? No. All that has to happen is the velocity time graph has to be what I say is approaching 0, right? It's moving towards 0, which means that it's slowing down, right? Moving towards 0. The acceleration time graph here is in the negative, and we'll go back to the question I asked a couple times ago and Joey answered. Can you tell from this that the car is slowing down? Can you tell from the acceleration time graph, because it's below 0, does that indicate the car is slowing down?
You can't tell that from the acceleration graph.
You can't tell it from the acceleration time graph only? Why not?
Well, it's moving backwards.
Exactly. Exactly the same situation that's happening right here, right? Here it's slowing down. I feel like I should be writing on here, should I? Here it's slowing down. But in this region here, it's what? Speeding up backwards. So you can't tell just from the acceleration time graph. The acceleration time graph does not tell you everything. Okay, so from 15 to 20, now we know that it's stopped. We can tell because it's flat. The velocity time graph is flat and at 0, so it's stopped. And the acceleration, did I say acceleration time? The velocity time graph is flat and at 0, so it's stopped. And the acceleration time graph is flat and at 0, which means it's either stopped or it's moving at a constant velocity. Lots to think about. Here it's doing what? 20 to 25, it's? Remember here it was stopped. Speeding up backwards, correct, Daniel. Speeding up backwards. Velocity is negative. Whoa, velocity negative, it's speeding up. Speeding up. backwards. If the velocity time graph moves away from zero, whether it's up above zero or down below zero, the car is speeding up. And the acceleration time graph is negative in conjunction with the velocity time graph. They're both the same sign, both negative, negative, negative. You can say it's speeding up backwards. Between 25 and 30, the car is constant velocity, right? Straight line. What's happening at this point right there, like 27.5 seconds? What happens? Crosses the origin, crosses the start line. Is that indicated at all in either of these? No, because it doesn't mean anything in the velocity or acceleration time world, right? So straight line here, constant velocity. Flat line here, constant velocity. Acceleration is zero, either maintaining constant speed or stop. And the last little bit, 30 to 35, is slowing down. Velocity time graph approaches zero, right? Acceleration time graph, because the slope here is positive, the acceleration time graph is above and flat. And once again, you cannot tell that it's speeding up or slowing down simply by that. Does that add to your level of understanding, do you think? Yeah? One more.
Acceleration graph is now the worst one.
Yeah, it's not easy. But, I mean, the idea is that when you're going from position to velocity, right, you always, when you're going in this direction, right, you're looking at the slope here, and you're graphing the value of the slope here, right? And when you're going this way, you're looking at the slope of the VT graph and graphing the value of the slope. For example, slope is positive, graphing it at positive. Slope is zero, graphing it at zero. Slope is negative, and then down here at negative. Slope is zero, it's at zero. Slope is negative, it's at negative. Slope is zero, it's at zero. Slope is positive, it's at positive. Yeah, well, when you just, it's just the slope, that's all it is, right? Going the other way is hard because you got to sort of reverse all your thinking, right? It's hard. It's hard. Could I give you the acceleration time graph and ask you for the velocity time graph? Is that possible? It would take you a while. Would you be able to, like, just if I just gave you this graph right here, could you tell me that it's for sure from 0 to there? No, why not? Because it could be there or it could be there. You have no idea, right? You have no idea. And in fact, I think we've even discussed this yesterday. If I just give you this, you really can't tell where on the displacement time graph it goes, right? It's not so much of a problem because the displacement time graph, you can just say, well, it's wherever it starts, we'll call that 0, right? But you can't just say, well, whatever speed it's at, we'll just call that 0 speed. That doesn't really work. So it's a little bit less important going this way. It doesn't really work. So, yeah. But you won't see any acceleration time graphs, and I won't say, do this. I might say, what shape is it? But I certainly wouldn't be able to say, flip off. Okay. I'll stop there. All right, so the multiple choice little test quizzy thingy here. What does a straight positive AT graph represent? Straight and positive. What does that represent? Say again?
C.
C is right. C, constant positive acceleration. 1 for 1, right? Uh-oh. Number 2. What does a curved, decreasing with steepening slope DT graph that is above the time axis represent? There's a lot of words there to put together.
C.
My answer key says D. Speeding up while moving left, and that is correct. How can you tell it's speeding up? Slope is getting steeper. So why is it not slowing down? Oh, because it's not slowing down, definitely not C. How can I tell it's not slowing down? the slope is getting steeper. It's steeper negative, right? But it's still steeper. Okay. We're learning it. It's okay. Three. What does a curved DT graph with flattening slope represent? D is correct. Nobody got a question about that one? Everyone's good with that one, it sounds like. Good? Okay, number 4. Number 4 says, what does a straight increasing line DT graph represent? Like so. What's your answer? A is correct. Well done. 6 looks like this. These are all DTs, aren't they? Oh no, there's a few. Oh, did we?
I can see.
I'm going to do 5. I haven't done it yet. 5 is what, Peyton? You would be right. Do I need to go through 5? Curved increasing DT graph. Yeah, that is definitely speeding up to the right. Right? Slope is increasing. Ask me if you're not sure. I need to know if I need to spend more time, or at least I'll look and see if you're erasing or whatever. 6 is like this. D, T. This is straight decreasing. C. Right you are. C. Constant negative velocity. Seven, straight negative AT graph.
B.
Emphatic B. 7, B is right. Well done. B, constant negative acceleration. 8, curved and decreasing, flattening DT graph, like so. That is A. It is. Are you feeling better about things now?
How do you know if it's going left or right?
Why is it going left?
I don't know if it's...
Okay, let's have a look at A a little closer. It's curved, it's decreasing, it's flattening slope, so it's definitely slowing down. And how do I know it's moving to the left? How do I know it's moving to the left? Because the slope here is all negative, which means it's moving to the left. Right? Lots of sort of different pieces of information you have to put together. V and T. Straight decreasing DT graph represent. I have C. You have C?
Why isn't that one left?
Why is that one not to the left? Good question. Why is that not to the left? Because the velocity is, the graph is above and it's in the positive region, and positive velocity means moving to the right. Yeah. There's so many pieces, right? Different than this. Dallas asked, why is it moving to the right? And it's because the velocity is above and it's positive. I will not try and tell you, oh yeah, this is easy. This is challenging stuff, right? I don't dispute that at all. It takes practice. That's why we're spending this extra day out here. What about 10?
We have to the right.
C. If I ran off another version of this, this is version B, if I ran off another version of this, would you want it? Or no?
Sure.
Yeah? Okay, I'll see if I can get to it to this period or not. I may not. We'll see. I think that's valuable, don't you, to sort of work through this stuff? Yeah. Okay, good. Okay, so now the next question is textbook. Page. No, that's not right. This one. Sure. Oh, sorry. Was there one particular question, Chris, on page 69 that you wanted to look at, or? 14, okay. Probably, if I got time, yeah. Oh, yeah, were you supposed to do all of them? I don't remember the numbers. 14 I have circled.
It said page 69.
Oh, yeah? I have 14 and 18 and 19 and 20 circled. Are those the ones? In my book. So which one, Chris? Just 14? Okay. You, it's in the book, but I think I ran off that page so you could draw on your graph, right? Didn't I?
Yeah.
I ran off a piece of paper with that on it. So I'm going to have to take a minute here and just redraw this graph so we can talk about it. Give me a second. Okay. And this is a velocity time graph. So like anytime you're doing any of these questions, first step, no matter what, is to identify what kind of graph you're talking about. Right? What kind of graph you're looking at, right? This is a velocity timer. It shows the speed and the direction. Describe the motion of the train, consider the direction, positive direction to be east. So what is this train doing? Well, here the velocity is increasing to the right, so it's speeding up to the right. Then it maintains a constant speed to the right for a while, and then it doesn't back up, but it slows down, right? Slows down. It stops for like an instant, right? It slows down, but then it immediately does what? Well, here it's slowing down because it's going to zero. Here it's speeding up backwards, right? Slowing down because it's positive velocity, it's above, approaching zero. Here it's moving away from zero, speeding up backwards. Here it's, I'm assuming that's supposed to be flat. Here it's maintaining a constant speed, and then it speeds up backwards again. So like it's like it left the city kind of thing, and now it's going faster. Okay, so now it says how fast is the train moving at each of these times in kilometers an hour. So you're just really reading the graph, right? I'm assuming you can do that. Okay. C, calculate the accelerations for the lettered sections A to F. So you would have to actually find the slopes. Do I need to do that one? Okay. So the first one's going to be 25 over 120, which would be like about, I don't know, somewhere around 0.2. What is it? 0.20 something? Okay, and then the next one, obviously, the slope is 0. Here we're going down 25, so that's going to be minus 25 over 420 to 300 over 120. So that's going to be minus 0.208. In that steep section, we're going down minus 75. And the horizontal is 420 to 540, so that's again 120. I can't do that one in my head. Someone's going to have to help me out there. E is 0. And F, we're going down 75 to... It doesn't quite look like it goes all the way to 150, though, does it? So it's like minus, I don't know. Who knows, right, what it is. Once again, here's a classic example where the person in the art department of the book thought that it would be just fine to just draw the line right to there, because it didn't look good going all the way down to the bottom. And meanwhile, the guy in the math end has the correct answer, and they changed the picture on it. But that never happened to me.
Negative 75 is negative 0.62.
Okay. How far, I'm looking at part D now, how far does the train travel in each of the lettered sections? Oh. Okay. I gotta erase all this. When they're asking for how far, what do they want you to do? Anyone? Come on, you guys gotta know this. They want you to find the area. That's what they want, right? How far? They want you to find the area. So that's going to be like This one's here is going to be half the base, which is 120, times the height of 25. So that's going to be 60 times 25. 6 times 25 is 150. I think it's 1,500 meters. Did I do that right in my head? Yeah. The rectangle is from 120 to 300. That's a base of 180. And the height is 25. 180 times 25 is the same as 104, 40, is it 4,200, something like that? 4,500? That triangle there, do I need to keep going or do you kind of get it? Actually, I want to do the bottom ones, for sure. Can you do this one okay? D is this triangle here, which I'm assuming you can do. E is this one here, but the hard one, oh, they don't have, oh, they do have an F, okay. F, how do we do F? You have to deal with that triangle there and that rectangle, right? Because it's all the way from the graph all the way up. Was that maybe the problem with that one? Right, so it's all of that, triangle plus rectangle. Okay, so here are the displacements according to the solutions. So 1,500 for A, 4,500 for B, 1,500 for C. D is approximately 3,900 meters, that triangle. E is minus 5,600 meters, and F, there's the triangle and the rectangle, 21,800 meters. Do I need to go through those, do you think, or don't just sort of go, I don't know what you're talking about. That's good? What is the total displacement of the train? So what do you have to do? Add them all up, right? So it's 1,500 plus 4,500 plus 1,500 plus 3,900, and then of course make sure you subtract. Where's E? Is it up here? Total displacement minus 2,300. And then the last question is, I think it's the last question. No, it's not. The average velocity for each of the letter sections. How do you find average velocity from a VT graph? You have to take all of those displacements that we just calculated and divide it by the time, exactly. So there's the 1,500 we just calculated divided by the time. There's the 4,500 we just calculated divided by the time. So in section A, it's traveling 12.5 meters per second, section B, 25, and so on.
So you can like add them all up.
No, you can't. Because the time, that would only work if the time intervals were always exactly the same. And you can't always guarantee that. So yeah, you have to do average velocity by doing displacement over time. Average velocity for the whole trip, you're going to take this total displacement right there, 2,300, divided by the total time, 720. So its average velocity is minus 33. And then in H, they try to fool you. What is the average speed for the trip? Average speed, what they want is, instead of displacement, instead of using negative values down here in displacements, you just use positives, right? I hate when I do this. Okay, so it's going to be, take the absolute values for all distances. In other words, ignore the negatives. So the total distance traveled is 38,800 divided by 720. The average speed is 54 divided by the time. Okay, so speed is just without direction, right? I need a few more nods to convince me that I've done okay here. Okay.
Are those in the back answers too? Is this from the back answers?
No, this is from the teacher solutions, but they are available in the white binder. And did someone look to see if they're available online or no? Did anyone look? No one looked? Okay, you're going to make me do it, aren't you? Okay. I will ensure that these are online by the end of today, because I actually saw I had a full folder here of solutions. So all my solutions are here in PDFs. I'll fire them up to Schoology today. Okay? So I'm going to give you the rest of the period. You got a few minutes left here, about 10 minutes. Ask me questions if you need to. We're going to move on Monday.